Okay, so yes, hello everyone. In the previous class, we already covered about the S and AR mechanism there, and you will get a question in the previous class. Okay, this is a question there. Can you just answer this question now? What is the question? In S and AR mechanism, okay, there's some options is given to you. Which one is going to react first, or what is the order? So, what are the options there? This is my NO2 group, and this is the fluorine, and similarly that this is the NO2 group and this is the chlorine, and further that is this is the NO2 group and it's bromine. If you attend the previous class properly, so you are able to answer this question. Yes, please. What will be the answer? Let's suppose this is my A, this is my B, this is my C, and this is my D. Yes, what will be the order? Yes, please. Who is going to react first in a S and AR mechanism? B, then A, then C, and then the Aditya. Oh, very good. In the previous class, we discussed about a point, yes or no. That in this case, the first step is going to be the addition mechanism. It means nucleophile first added, and then there is a generation of negative charge. So fluorine stabilizes that negative charge more. Okay, so what is the actual correct answer for this question is what? That fluorine stabilize the negative charge first because it follow the addition elimination mechanism. If you want to like understand the mechanism, please watch the previous class. So it's an addition have to be there. First of all, addition is the rate determining step, you can say. Okay, so this is my addition, and then there's a elimination take place. So addition, elimination. Okay, so what will be the correct answer for this question? That is A, then B, and then C, and then D. Okay, Aditya, are you getting this point now? I hope it is clear now. So let's see the next one, the last one in the reaction intermediate one, S and I mechanism. Okay, so let's just discuss about the S and I mechanism there. So what is the meaning of this? S for substitution, N for nucleophilic, I for intranuclear, you can say intramolecular, you can say. Okay, so it means that is a nucleophilic substitution reaction inside the molecule. Yes, you can say. So, for example, it's one of the famous one that is you can say the DASA is the name of a reaction, but for this class only name is not much important that much important there. So let's see that how would the reaction look like. First of all, you will be having some OH. It means some alcohol. Okay, we are using SOCl2 as a reagent, and then there is a formation of RCl. Okay, so this is a simple. This reaction is going to follow normal that SNI mechanism there. Okay, I said SNI, I for intramolecular, for S for substitution, and for nucleophilic. So it's a SNI mechanism there. So let's just discuss about there. We are basically going to discuss about two cases. Okay, yes, this is a very famous one. Two cases have to be there. So let's discuss about the cases one by one. So let's just talk about the mechanism. Okay, how the real mechanism look like. Let's just consider an example. Okay, let's just consider an example. What is going to happen there? Let's wait for 1 minute. I guess everyone is joined now. Okay then. So let's continue now. So what was the example there? If let's suppose you are having this carbon and this is connected with some OH group there. Okay. There you can consider anything. Let's just consider this is my CH3 and this is the CH2 and CH3. Okay, and this is some hydrogen is there. So first of all, this oxygen has a lone pair. Okay, how about the SOCl2 look like? You are having a double bond. This is chlorine and this is chlorine and like this. Okay, so the step number one. Everyone you know that here there is a lone pair present, and whenever the lone pair present there, they start attacking. Okay, this lone pair attack here, this bond, this chlorine leave the molecule. Okay, I'm repeating one more time. This oxygen has a lone pair attack on a sulfur, and then chlorine leave there. So how about the case there that chlorine leaves? So that's why you can write minus of Cl. It means it is leaving the molecule. Okay. Next step is going to be the, let's just consider this group like a R so that we are able to understand. Okay, I will tell you this stoichiometry in a while. Just for this part only, let's just consider this is some R group there. Okay, RH you can say. So it is going to be the R combined with this oxygen and sulfur. This is the sulfur, double bond and chlorine have to be there. So this is the meaning of this first step here. It's a very simple step. OH has a lone pair, attack here, and then chlorine leave, and then we are getting ROC, SOCl is there. Okay, now let's see the next step. That how about the next step is there. So let's just again spread the R. How about the case there? So first of all, this is some carbon. Okay, and the same example I'm taking in order to explain the mechanism. I'm taking R there. Okay, like this, and this is some hydrogen as well. Okay, and this is O, SO, Cl. Okay, see, right now when we are dealing with any kind of mechanism right now, some nucleophile is there, nucleophile adding from outside, but in this case no nucleophile is adding from outside. The chlorine itself behaving like a nucleophile. So whatever the case, why the name of the reaction is going to be the SNI intermolecular reaction there, because this is my chlorine and this chlorine, see, attack here. Okay, this chlorine attack here, and this is how it's leave. Okay, it's leave chlorine attack here. So let's see what is going to happen. This carbon is combined with the chlorine, and this is the CH3, and this is the CH2 and CH3, and there is a hydrogen there. Okay, and what is going to happen there? This chlorine uh, attack here, and we're getting SO2 plus HCl. How about the HCl there? From the previous one, this chlorine, okay, this chlorine form a bond with this hydrogen there. It means HCl. So these are the side product, that is SO2 plus HCl is there, okay? So there's a two side product. And what is the good thing about this? This is also the gaseous state and this is also the gaseous state. Maybe you already know in the very first class of the haloalkane and haloarene chapter, I told you about this, that SOCl2 reaction is one of the famous one. Why? Because both side product are gases in nature. It is gases in nature evolved out. It's also the gases in nature evolved out. Okay, sorted. Now, what is so special about this mechanism? Do you know what is so special about this mechanism? Let me just move here. Look at this. OH group connected this side, right? The same Cl group connected this side. In this case, in this kind of mechanism, retention of configuration take place. This is a key point here. That is retention of configuration. Okay, I hope you know the meaning of retention now, that before and after the reaction, the thing, the stereochemistry is not going to change. So here there's a retention of configuration is there. This is very simple. It's a retention of configuration take place. Okay, that's it. This is all for the mechanism. But in the same point, in the same type, there is a one more case also present there. How about the one more case? What is the meaning of this point? That is one more case there. So let's just discuss about this point here. That how about the one more case there? Listen my point. If the second step is going to be the case number two, okay? Case number two, I will tell you why this is a case number two. In this case, along with the Cl2, we are adding extra point, that is pyridine. Okay, this is pyridine. Maybe you already know in the very first class, I told you about this, that if you are using pyridine with the SOCl2, it's going to follow the SN2 mechanism. Okay, so listen, if pyridine there, the same reaction have to be follow SN2 mechanism. And we know what is going to happen in SN2 mechanism. In SN2 mechanism, there is a inversion of configuration, retention of configuration. Yes? Anyone? Retention of configuration or inversion of configuration? Yes, very good, inversion. Okay, so yes, what is happening there? There is an inversion of configuration take place. Okay, sorted. It means here we are end up with the inversion. Yes. Okay, see the difference, that if you have to observe only SOCl2 there, there is a retention of the configuration. But if with the SOCl2 we are using pyridine, it is going to follow the SN2 mechanism. But the question be like, why? Why it is going to follow the SN2 mechanism? Okay, so let's discuss about this point as well. So let everything copy and paste. For example, again you are having this OH group, there's a some three group have to be there. This oxygen has a lone pair, and still this is SO and Cl there. The mechanism looks similar, same. So this attack here, okay, this chlorine leave the molecule. How about we are getting that is this O combined with SO and Cl is there. Okay, sorted. So it means this Cl have to be released. Yes, technically what is going to happen there? This oxygen combined with the chlorine and we are getting HCl. As we discussed already in the previous mechanism, it means HCl is the side point here. It means the chlorine which leave the sulfur here present as HCl form. Yes, it is present as HCl form in the previous case. So now what is so special this time, like why we have to follow the different trend here? Look at this pyridine. Okay, you know what is pyridine? Pyridine is a acid or a base. Yes, please, anyone? This is acid or a base. Base, right? Why obvious this one has a lone pair there. So this pyridine is a base. So pyridine be like HCl, you are acid and I am a base. Why not we can combine? So what is happening? This pyridine which is present in the reaction now form a pyridinium ion. Okay, like this. There is a formation of pyridinium ion. So what is going to happen then? If this is combined with hydrogen, we are getting pyridinium ion, right? Done. And wait. It means this chlorine is now free. Yes, this chlorine is free. So chlorine be like, what should I do? So this time, look at the difference between this and the previous mechanism there. What is so special here? What is the difference between these cases? Now chlorine be like, let's behaving like nucleophile there. Okay, so what is the different point here? That here chlorine is behaving like an extra nucleophile. Okay, so let's see what is going to happen. This chlorine be like, should I attack? But this chlorine be like, no, I have to attack because now I am free because pyridine is present there. So it means that this chlorine is no longer the part of a reaction. No, it is not going to participate. Then what is happening? This chlorine basically attack here. Okay, so let's see what is going to happen. Let me just erase this. This is the extra point. Okay, so what is happening there really? That let me just write like this. Okay, this chlorine is like this. Okay, so it form a bond, isn't it? The same kind of thing we discuss in a SN1 mechanism, SN2 mechanism there. This is dotted. What is it? It is a transition state. It is a transition state. So what is going to happen there? That this is very simple now. This group going to leave and we are getting this carbon and this side chlorine connect here. So see the difference between this and the previous one. Here are OH, I'm sorry. Okay, look at this. This side, the OH is connected here. Look at this. This OH is connected here, but now the same chlorine connected opposite side. So what is it? It's an inversion of configuration. So be noted, it is one of the famous reaction. The name of the reaction, if you want to note it, let me just write the name of a reaction. It's a Darzan reaction. Okay, naming reaction, important one. Yes, it's really very much important. Darwin reaction. So it's very much important. Question already asked so many times from this concept. If you're using only SOCl2, it follow the SNI mechanism. But if you to use the pyridine in the same reaction, it going to follow the SN2 mechanism. Inversion of configuration take place. Okay, any problem with the SNI mechanism? Please, anyone, please ask. Okay, that's it. This is all for the reaction intermediate topic. Okay, so let's start with the left part here, that is haloalkane and haloarene. Let's continue. So let me just quickly give you a brief. In the previous class, what we discuss about some important part, that what are the uses, their preparation. In the preparation part, we just finished the preparation with the alcohol. If you want to observe this point, we already, this is the last topic which we covered in the very first class, that the percentage of the bromine in a chlorine. Okay, if you want to watch this again, please watch the very first video of the YouTube there. Okay, so we already covered this point there. Okay, that's it. Now let's continue with the new topic here. In today's class, the very first topic of discussion is the preparation of alkyl halide from the alkene there. Okay, preparation of alkyl halide from the alkene. Let's cover this slide later. Let me first explain what is really going to happen there. Okay, so first of all, there's a 2 point. First of all, it's going to be the symmetrical alkene system. So what is the meaning of this word symmetrical alkene system? If let's suppose I'm having a carbon double bond, and basically this is connected with some CH3. Okay, CH3. So it's a symmetrical because obvious the double bond, same thing both side. Okay, one more. If let's suppose you're having a carbon and let's suppose the two hydrogen connected like this. So obviously again it is going to be the symmetrical alkene there. Okay, so thing is very simple there, that okay, it's sorted for the symmetrical one, but the next point is going to be the asymmetrical or unsymmetrical. So what is the meaning of this word unsymmetrical alkane? I will tell you like why I'm explaining all this silly thing to you, because we are going to use it. So again, if you are having a carbon-carbon double bond, let's say it is connected with some CH3, and let's say this is hydrogen only like this. So see this, if you have to observe this, this is the double bond, and this side we are having a carbon, and this side we are having only hydrogen. Okay, I hope the symmetrical and unsymmetrical part is clear for you. Okay, so let's just back again. Our 11th class, one of the famous one, Markovnikov addition. Okay, Marconic addition reaction there. So let's just quickly recall what is happening there. If you are having some carbon-carbon double bond, okay, if you are having some carbon-carbon double bond like this, and if I'm using HBr, if I'm using HBr, we have to follow the MV, means Marconic of addition. Okay, if you don't know that, this is the name, that is Marconi rule. Okay, what is the meaning of this rule? This rule simply told us about that the negative part of the adding molecule. It means in this H positive and Br is going to be the negative one, right? It means negative part of the adding molecule. Okay, so negative part of adding molecule was going to add the negative part of the adding molecule combined with that carbon, which one has a less number of hydrogen. Okay, which one has a less number of hydrogen? This is the simple meaning of Marconic of addition. So basically what we are going to get here, that we are at a with, this is my carbon. Okay, let's say hydrogen is connected here, the bromine is connected here, and like this. Okay, thing is very simple. If it is a symmetrical alkane, the problem start when we are having a asymmetrical alkane. Okay, so let's just back. How about the case here? Hydrogen, hydrogen, and hydrogen, and see, this is hydrogen, hydrogen, and hydrogen there. Okay, then, so let's continue further. Let's see one more kind of example there. Okay, so let's observe this. If, let's suppose, let's discuss with the mechanism, right? Mechanism is also important here. And again, in organic chemistry, please don't try to understand the mechanism directly. No. Okay, first of all, you are going to understand the mechanism properly, and then we have to further move further. Okay, so let's see how. First of all, let's discuss about the mechanism part here. How about the mechanism? So let's suppose you're having some carbon-carbon double bond like this, and you are having HBr. Okay, so what is the step number one here? The step number one is very simple, that if let's suppose this double bond attack here on this H positive. Okay, so basically we are just assuming that it's not a ionic bond. First of all, it's a covalent bond. You can say in this HBr, this Br have a partial negative charge, and the H positive has a partial positive charge here. It means this double bond simply going to attack on this H positive. Okay, so let's see what is going to happen there. That in this case, there is a formation of carbon H positive, obviously it's going to attack. So just assume like how the thing is going to happen there. It means just think about it like this. Okay, let's just back here. So what is happening there, that you can assume this bond break like this, and here we are getting a negative charge, or let's say this is a positive charge. It means, think about it, the positive combined with negative, right? So just for this, assume, this is just for assumption part only, it's not really happening. Okay, every time think like that. Otherwise, this is a very simple mechanism. The double bond attack on H positive, and let's move further. So what is going to happen, this H positive connected here like this, and this carbon has a positive charge. Maybe it look very weird, ma'am. Why we have to follow the mechanism if we already know the rule? Yes, I know it is simple. But do you know, when we start following the rule, it will be very difficult for you. I will tell you why. Just for this, wait. Then we are having a Br negative. So this is positively charged, this is negatively charged, attack here. And basically the Brahmin is going to connect here. And okay, this hydrogen is going to connect here like this. Okay, it means this is a final product here. Now it is your turn. Please answer this question. Okay, there's a question for you. Just try to answer this question. Okay, this is a question for you. If you are having a carbon double bond, okay, yes, please answer this question. Same, you have to add HBr in this case. Okay, maybe you're not able to answer this, right? Let me just give you some options. Option number one, okay, this is B. Yeah, you can change the position of the CH3 group. It is not a big deal. Okay. Yes, which one is the feasible answer? Is it option number A or is it option number B? Yes, please. B, 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 B. Okay. Are you sure? Okay. Yes, very good, everyone. It is going to be the answer number B there, right? So why this is the correct answer here? Because the rule said the bromine is going to connect with this carbon, which one has a less number of hydrogen, right? I said less number of hydrogen. So between this and this, if you to compare the position here, so what we are getting basically, this one has a two hydrogen, right? And on the other hand, this one has a zero hydrogen only. So it means this is a feasible attack, right? So it means bromine is going to connect here, not here. Okay, please be noted. It's not like this is not going to be the product, but problem is what? It's a minor product. Most of the time in organic chemistry, our main focus on a major product. Okay, because sometimes the examiner play very smartly. Sometimes you are end up with a minor product as well. Okay, that's it. This is all for the slide. That preparation part here, preparation of alkyl from the alkene there, you will be having some alkene and then hydrogen halide. It can be HI, it can be HBr, it can be HCl, and it can be HF. But did you know? Do you know, I'm sorry, that this is not going to participate? I'm sorry, it is not visible. Okay, this is not going to participate, and even this is also not going to participate. But why? HI and HF is not going to participate in this reaction, but why? Most of the time we are having reaction only with HBr and HCl. Do you know the reason behind this? Who is very reactive, Hasio? Okay. And then how about the HI? Okay. Yes, very good, Jaya. So, yes, what is the important point here? If you have to observe this point here, let me just explain this thing to you. That if you are using HI, let me just back here. Okay. So, if you have to use HI, so what is the problem with HI? You know, HI quickly break. Okay? Quickly break. So we're getting H positive and I negative. So I didn't be like, no, I can't form a bond with the hydrogen. Then we'll be like, why not with the carbon? I'd be like, no, 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 no. Carbon is very small in size and I'm very large in size. Okay? I'm not going to form the bond. Iodine, instead of forming this, quickly form a I2 there. It means the reaction is not that much visible here. And the second point, if you to deal with the HF there, so HF is very explosive in nature. Okay, so be noted whenever we are dealing with halogens. So fluorine and iodine is not the topic of discussion in some time. Okay, yes, some special cases can be there, but not every time. Okay, then. So let's see a question. Okay, try to solve this question, everyone. This is a question for you. Question said you have to use some X, and yes, here you're requiring some knowledge of the 11th class as well and 12th as well. Okay, so there is a some H2Br and the X have to be there. Product you are getting some Y, and then we are end up with this. Okay, you can solve this question smartly. Okay, I don't know, let's say X, but at least I don't know that what should I take Y so that we are end with the that last product. Okay, think about it. 1 minute for your time start now. Please answer the question. Okay, okay, maybe I'm blocking your view, so let me just, oh, I'm sorry. Yes, please now. D. Okay. B. Okay. B. Okay, even you can solve this question just by a key point. Just by a key point. Okay, if you are having a problem with any other option apart from the D, I can admit, but like how you're getting option number D is the correct. Okay, no thing, no need to say sorry. Okay, then let's find out the answer. So most of you are very correct here. So let's see what is the answer for this question. So first of all, see, if you're observing something that we are basically starting from some bromine there. Okay, I know one thing that surely here we are ending with this kind of thing, CH3. CH double bond and CH2. Then and then you're able to follow the Marconic addition. So what is my Y? Y is going to be the HBr, right? Because we just discussed about the mechanism, like how about the reaction is going to happen. So let's just drop the X, let's just focus on a Y. HBr acetic acid, okay, it can be the answer. HBr acetic acid, it can be the answer. But option number B, Y, and like this is not the correct answer here. I will tell you why. Because maybe you already know the 11th class topic that if you're having a carbon-carbon double bond and if you're dealing with the bromine, so what is going to happen there? This attack here, and there is a formation of this kind of brominium ion formation take place. And now the next step is going to be the one more bromine is there. It is an anti-attack, and there is a formation of dihalide. Okay, here we are end up with the vicinal dihalide. So no, we are having only one bromine here. It means this is not going to be the correct answer. Yes, definitely not correct. So option C and option D is no chance. Okay, this topic is from the hydrocarbon of the 11th class. So if you are not able to understand this, please focus on 11th class. Not correct, not correct. Now between option number and option number B. Okay, so let me just tell you what is really happening in this case. What is the extra point basically in this reaction? Okay, so let's just discuss about this extra point. Okay, so basically you are having CH3, okay, and this is a CH2, and this is some CH2, and this is Br, bromine. And now be noted, in this reaction we have to follow the elimination reaction, okay? We have to follow the elimination reaction. So what is the meaning of this word elimination reaction there? You know, basically what is happening, just I'm explaining how it is going to happen there. Let's suppose this is my hydrogen, like this. Okay, this bond move here and this bond open up. Okay, so technically we are getting that is a carbon carbon double bond like this. Okay, and okay, it's going to be the CH3 there. Okay, so basically this is a assumption. This really we are going to get if we are to follow the trend elimination reaction. But now question be like, see in the reaction you are having QH. Okay, QH. Now KH can do two things. What is the condition number one? QH be like, okay, I am a ionic bond. You know, potassium is there. So it is a positive charge, it's a negative charge. And if you know in the previous class we discussed about the OH negative and water, right? Yes or no? That OH is a very good nucleophile. OH is a very good nucleophile and water is a very good living group. So question be like, why not OH came to the picture, attack here and open up the bond? Okay, so question be like, why not in this case we have to follow the substitution reaction? Okay, I'm sorry, not like this. Okay, so what is happening that why not OH connect here, and that is this is a CH3, it's a CH2 and CH2 and OH. Question be like, why not this product? Why only this elimination product? Right? Because this is the point. I'm not saying you are not going to get, but the question asked about like how to select so that we are getting this is the product. Now listen this point. If you want to follow the elimination reaction, if we are requiring elimination reaction, so how to select a elimination reaction over a substitution reaction? So be noted, there is some key point that how to select a elimination reaction. If you want to check it, is it elimination reaction or not? So first of all, you have to check it for a strong base. The base have to be very strong. Strong base. Then you be like, ma'am, K positive and OH is a strong base. I know this is a strong base. The condition number two, that heat, temperature have to be there. Okay, every time you are using this kind of the symbol there, you can say it's a high temperature. So most of the time, these are the key point is mentioned to you that heat or like strong base. Okay, sorted. Now in option number A, you are given with the aqueous KOH. Okay, in the option number B, you are given with the alcoholic KOH. Now, it's your turn. Can you just tell me who's going to be the very good base? Is it water, like aqueous KOH or alcoholic KOH? Like, how about the case? In this case, you are having water plus KOH. Okay, in this case, alcohol, let's say any alcohol, let's just consider ethanol. CH3, CH2, and OH. If you're having a very good knowledge of the acid and base 11th class, you are able to answer this question. Which one is a good combination of a nucleophile? Let me just give you the option, option number A or option number B. Yes, please. A, A, B, B. Okay, so let me just tell you, yes, the answer is going to be the option number B. Now, why the option number B is the correct here? Because here we're having a ethanol. or alkyl you can say. So what is going to happen there, that this is a CH3 and this is a CH2 and this is a O negative, and now potassium form a bond and the water molecule evolved out, right? So yes, this kind of base in organic chemistry is going to be the strong base, very really very strong base. But on the other hand, in this case you are having only the water, so water be like, okay, I'm also a base, you are also a base, why not, let's combine. You know what is happening, water start interfering in a reaction. So KH will like, leave that, I will give my OH, it's behaving like a very good nucleophile, you know, that if you are having a KOH in water, so there's a two option for you. So do you have to go with the nucleophile, or you can say you can go with the base. We discuss that KOH be like, you know, there is a competition is going on, water and KOH. So KOH be like, I'm having OH negative and you are having water, and in the previous class we discussed that OH is a very good nucleophile, so that in order to reduce the competition it is behaving like a nucleophile. So be noted, whenever we are having alkylic QH, then and then it's behaving like a strong base. It means it is going to be following the elimination step. Okay, so this is very simple sorted explanation here. Let me just back what we are discussing, right? A question. Okay, so let's just back here. So what is the correct answer here? The answer is not going to be the diluted one, the answer is going to be the that concentrated. Okay, that's it. This is how you to solve the question. It's a 11th class topic, but although this is a question, that's why I'm explaining to you. Okay, so very good, who's just answered the option number B is a correct answer. Any problem left, please let me know. Okay. Yes, of course, Hasio. Okay, because there is a competition between the water and OH1, so better to behaving like a nucleophile as compared to the base. Okay, Hasio, are you getting now? That's it. So let's continue further. Let's see the one more point. Then let's see the next preparation, preparation of dihaloalkane. Okay, as we just discussed about this mechanism, the same mechanism is there, that if you are having a double bond and if you to have at the halogen. Yes, one more important point there. This halogen we have to use with the non-polar solvent only. Okay, non-polar solvent. And you know, it's a, one of the famous reaction, maybe already familiar with this word, that is a bromine water test. Okay, maybe in organic chemistry lab you all already covered the same test, that bromine water test. This test is very famous in order to identify the unsaturation in a compound, like it is a double bond or a single bond or a triple bond, right? And one more important point, these are the part of the 11th class, I'm giving you a brief. X2, the halogen should be present in non-polar solvent. Second, most commonly we are using bromine. Most commonly we are using bromine. Bromine is a bromine water test. It's a unsaturated. Bromine water test, it's a test for detection of unsaturated thing. Now one more question for you. Okay? This is my benzene. Oh, I'm sorry. Okay, yes, please answer the question till then. Benzene is going to give the bromine water test positive or not? There is any positive test for the unsaturation for the benzene ring? Yes or no, please? Yes, okay. So, Abhiyan, you completely missed the learn class topic, right? Come on, benzene never ever undergo the addition reaction until or unless we are having some Boss condition, right? Remember or not? That if let's suppose this is the benzene there. Okay, what is the meaning of addition reaction? This is benzene, and if let's suppose I'm using a bromine, so basically we are getting this is my bromine and this is my bromine, right? Like this. Is it feasible? No. Bromine will be like, no, I'm already okay. I'm aromatic compound. I can't react with the bromine there. So be noted, benzene never ever give the positive test for the bromine. One more reagent, if you remember, K-4, right? Bayer reagent, aqueous K-4. These are two one of the famous tests, just in order to check it the unsaturation of the organic compound, right? If you don't know, please go for that again, 11th class. So anyway, that's it. So what we're discussing there is some important key point for this reaction. That one we just discussed, with halogen, you will be having a non-polar solvent. Now the question be like, why there is a non-polar solvent? Because answer is very simple. For example, if let's suppose I'm having chlorine with water, so chlorine and water be like, why not we can form a acid? You know, HOCl acid, remember not oxo acid of the chlorine, very reactive. Okay, so what is the problem? That if you're having a carbon-carbon double bond now, so if there is a polar solvent present, it is combining with the Cl2 and there is a formation of OH negative and Cl negative ion, right? So what is happening? That is Marconic of addition. So then this bond be like, let's connect one OH bond and one chlorine there. No, no, we don't want this. We want that is the dihalogen formation there. It's wrong, it's wrong. So this is the first point, that why we are using that non-polar solvent, because extra point have to be there. Okay, condition number two, that most of the time we are using this reaction for bromine, like it's a famous test, bromine water test. Now my question to you, why not the test for the fluorine? Okay, the same answer, ma'am, it's explosive. Okay, iodine because it's very stable, not going to react. Okay, my question to you, why not chlorine? Like, why not chlorine water test? Yes, this is my question. Why not chlorine water test? I hope you already know that how much you can say this harmful the bromine. It is really very harmful as compared to the concentrated H2SO4 as well. Yes, please. Why not chlorine water test? The answer lie in your common sense. Okay. Hint for you, in your laboratory you are able to get the chlorine water. No, no. No, it's not like Aditya. Because in laboratory there is a no liquid form of the chlorine. Chlorine is a gas. You know, we are not able to trap the gas. So that's why in laboratory we are having only bromine. So that's why we have to follow the bromine water test. Okay, it's very simple answer, common sense question. Okay, so that's it. It means bromine water test we're using there. Yeah, you can go with the chlorine as well, but most of the time it is for the bromine. So let's just back here. Now let's start with the, not the slide. Okay, let's start with the reaction there. So this is a general mechanism there, but the question be like, how about the mechanism? How about the mechanism there? So let's just discuss about the mechanism part. Although we already discussed about the mechanism, but let's just discuss one more time. First of all, that the step number one, formation of halonium ion. Okay, halonium ion, or better to use cyclohalonium ion. I will tell you how about the case. That is, first of all, it's a formation of, okay, so formation of cyclohalonium ion. So what is the meaning of this word? That is a formation of cyclohalonium ion there. So for example, if you are having a carbon-carbon double bond like this, okay, you will be having halogen. Okay, so first of all, don't consider be like that one halogen. Let's suppose I'm having a bromine and bromine. So one bromine, I'm sorry, Br2, and one bromine has a negative charge and one bromine has a positive. No, nothing is not like that. You know that in halogens, only weak van der Waals force of attraction there, that is the London forces. The weakest form of the forces, intermolecular force of attraction, is the London forces. Then what? Who is going to do this then? You know, most of the time we're using that is a CCl4. That you can say CCl4 is there. Non-polar, yes, it's a non-polar. You can use that as CHCl3 as well. Okay, but CCl4 is the most commonly used here. So what is happening? That the CCl4 approaches like this. This is for understanding purpose only. That this is a carbon and hydrogen, chlorine, chlorine, and chlorine. Okay, again, it is just for only understanding there. So let's see that chlorine approaches like bromine. Why not we can come? Okay, what is so special about bromine? Bromine will be like, okay, okay, chlorine, let's combine. So just because of this, that chlorine start pulling the lone pair here. So what it means that this bromine achieve a negative charge, right? Something more is the number of electron there, and this one is partially positive. And this quickly attack here. This is just for understanding only. Again, I'm repeating, it's not really the mechanism, it's a concentrated mechanism. As soon as the you can say attack there and the bond leave. Okay, so this is a step number one. This is how the reaction is going on. This is for understanding only. So let me just write this like how, but the next step there, we will be having a carbon-carbon single bond and this X connected here. And there is a partial positive charge. Okay, so is it a three-member ring? Observe this, it's a three-member ring. It's a three-member ring. Cyclic, obviously it's a cyclic. So what is the name for this one? It is going to be, let me just erase this now. Okay, so the name for this one, this is my bromine, this is my bromine. It is known as a cyclo. Obviously cyclic structure, and halogen. Halogen has a plus charge. It is known as a halonium ion. EMY because obviously the positive charge. So cyclohalonium ion is there. Okay, this is a step number one. How about the step number two? One more halogen came to the picture. So let's see how about the next step there. Let me just raise this. One more halogen is going to attack. So look at this. It's follow the anti-elimination. Please be noted, it is going to follow the anti-addition. I said elimination, I'm sorry for that. That anti-addition. So what is the meaning of anti-addition? If halogen attacking from here, so this is how the ring open up. Okay, anti-attack. So let me just explain how about the next step there. That if this halogen is like this, so the second halogen be like this. It is one of the famous one, anti-addition. So halogen attacking opposite from the opposite plane here. So let's just observe this. This is already written here. How about the addition reaction in this case? Noted this. Addition of halogen to alkene is an example of electrophilic addition reaction. Yes, first of all, why the name is electrophilic addition reaction? Let me just back here and let me explain why. Because see this. This is a double bond. You know it's a very much electron rich. So many times we discuss about electron rich. And this bromine got a partial positive charge as a negative. So basically we are attacking on a electrophile. So it's a electrophile bromine attack on a double bond. So it's a electrophilic addition reaction. Okay, step number one. So this is a meaning here written here that the step number one is the electrophilic addition reaction. Second one, it involves a formation of cyclic halonium ion we just discussed, and it is a non-classical carbocation. Very good question. What is the meaning of this word cyclic non-classical carbocation? You know the general one carbocation how it's look like this. Remember planar one? In the previous class we discussed about it's a planar carbocation there, right? If it is a planar, it's a classical, yes. But see this. In this case, we are forcing the positive charge. See, it's in a three-member ring. You know very well, positively charged is a sp2 hybridized, right? And what is it? If it is sp2 hybridized, the angle have to be 120. And we are forcing a 120 angle in a triangle, it means 60 degree, so much hindered. It's a non-classical type of carbocation because here we are observing a angle strain. So it's a non-classical carbocation. It is not like a normal carbocation. Okay, this is a simple meaning of this word, non-classical carbocation. Okay, cool then. So observe this. This is how the reaction look like. You are having a carbon double bond, bromine CCl4 as we discussed already, and there is a formation of bromine connected. It's a vicinal, that is a dibromide there. There's a two step. We just discussed about the mechanism. So the step number one, formation of halonium ion. Step number two, attack of the X on a halonium ion. Okay, it is going to follow the anti-elimination addition. So let's discuss about this part because I'm repeating again and again anti-addition, sin addition. But this is the real meaning of the sin and addition. So sin, you know, sin means same side. Sin means same side. Anti means opposite, right? We discussed this thing so many times. Anti for opposite, sin for same side. Okay, so this is a stereochemistry of the addition reaction there, that is anti-uracil. For example, if you will be having a carbon-carbon double bond and the adding molecule attacking from the same side, if you to observe this point here, that this X connected from this and Y from this same side. So addition of two substituent to the multiple bond carbon from a same side of a multiple bond is known as a syn addition. Okay, if you to observe this kind of thing here, X and X both on a same side. See, this is both on a same side. Syn addition, yes. Let's move further. Observe this anti-addition, opposite side. If you have to observe my adding molecule, X is adding above the plane and Y is adding below the plane. So addition of the two substituent to a multiple bond from opposite plane. See this in this kind of representation. So horse is the projection. I hope you already know the projection part from the 11th class. So it is anti there. So it's an anti-addition, you can say. So let's get a hang of this. What is really happening there? So observe this. First of all, you are having methyl and ethyl is connected on the same side. Yes. First of all, my question to you, is it cis or trans? This molecule. I'm asking about this. Is it cis or trans? Yes, please. Is it cis or trans? Cis. If you're doing this, you're wrong. Okay, why you're wrong? Because see, it's not same group. You know, for this kind of thing, we are using a different kind of nomenclature. I will tell you how about the new nomenclature here. For example, if let's suppose I'm having a carbon-carbon double bond, okay? Let's suppose this is my chlorine and this is my bromine, and let's say this is my hydrogen and this is my hydrogen is there. Right then. So what is really happening there in this rule? In this one, yeah, you can say, ma'am, it's a cis because hydrogen on the same side. But my question to you is chlorine and bromine isn't the same. Then why it is a cis? Okay, so answer is very simple. Listen, this is a new case here that it's known as a new type of nomenclature. Cis becomes Z. It's a G type of configuration. Cis becomes Z. And how to identify? Here you have to prioritize the group. Okay, we have to assign the priority. How to follow the priority? Remember in the very I guess second class or third class we discussed about CIP rule when we're discussing about R and no, S nomenclature. I guess second video, third video, I don't know. Okay, so there CIP rule, priority there. So what is the priority rule said? First of all, you have to give the priority to the atomic number. If there is a tie, you have to follow the mass number. If there is a tie, okay, so you have to follow the that duplicacy rule. We already covered each and every point. So between hydrogen and chlorine, if you have to go with the atomic number, if you have to go with the atomic number, hydrogen is one atomic number, for chlorine it is going to be the 17. So which one priority is first? Obviously the chlorine. Chlorine and then hydrogen. Okay, similarly, between bromine and hydrogen, who's going to prioritize first? That is bromine. So it's a 1 and 2. So this time we are not going to say it's a cis. The same priority group on the same side, it is going to be the G type of nomenclature. Similarly, now for the trans configuration, now we can't use trans here. In fact, we are using E. Okay, it is E. Maybe you already observing so many times that E to E. Okay, this kind of thing in a nomenclature as well. Okay, so it's a new type of nomenclature. If the same group is not there and something present at a cis position, so the final answer have to be Z or E there. Okay, so technically you're right. So let's just back here. Now the same question is it's Z or E there. So your answer will be like, ma'am, cis. But no, it's not cis. It is going to be the Z type of configuration. Okay, Z. Okay, let's move further. Unsymmetrical alkene, bromine is there. So there is a two choices. If let's suppose you were to add this bromine from the wedge position. So yes, your second bromine have to be the wedge position. Anti, okay, it's attacking above the plane, it's attacking below the plane, so it's what anti condition. Or maybe you'll be like, no ma'am, we have to do opposite. Why not this is from this side and this is from this side? Yeah, you can do this as well. Okay, so in this case what you're observing that one is attacking above the plane and below the plane, and hey, they are racemic mixture of one another. Okay, racemic mixture we are not able to understand. Remember in the previous class we discussed about that if R and S both kind of thing present there, we are end up with the racemic mixture. Okay, 100% racemic mixture. If let's suppose this is 50%, this is also 50%. So it's moving clockwise, one is anti-clockwise, both combine and we end up with the racemic mixture. Yes, now this is a question for you. Can you just tell me the plus one is R or S? Okay, so let's try to find out for this. This center. Can you just tell me is it R or S? Apply your RNS nomenclature, please. This orange one. Is it S or R? What? You don't know? R. Okay. If you're not able to understand, please watch the RS nomenclature. I already explained there. So let me just explain how about the different kind of okay number. So priority wise, bromine got the first priority. This group the second priority. This one is the third priority. So let's rotate the plane. So basically what we're getting there, 1, 2 and 3. So what is this? This direction is this. It's a clockwise or anti-clockwise. It is a clockwise. If it is clockwise, H is a wedge position, yes. So it is going to be the R. If this is R, so definitely it is going to be the S. Okay. So be noted if let me just erase this, that if this is the R, if this is the R, it is going to be the S because both are just in different position there. Similarly, you can go with this. That is, this time our hydrogen at the wedge position. So let's find the configuration 1, 2, and 3. So it's a anti-clockwise. Technically, it's going to be the S, but what is the problem? H at the wedge position. So it's become R. So this is also R, this is R. R R and SS. right? I hope you are not now getting why it's known as a positive. Positive means R, negative means S. Okay, so that's it. This is all for the like symmetry there, and this is all for the anti-rule there. Okay, that's it. Let's move further. Let's see one more example there. It's an asymmetrical alkene, and in order to understand in a Sohos configuration, you can observe this: the bromine and bromine entane. Here this bromine top, here this bromine bottom, or you can revert. This is bottom now, or this is top. Okay, that's it. This is all for the asymmetrical. Sorry, this is all for the addition of halogen in a asymmetrical alkene there. Okay, this is all for the today's class. Now you are done. Any problem, any doubt, please ask. Okay. Yes, please. We'll continue in the next class from here only, okay? Next preparation method. So now basically we are done with the preparation from the that is alkene system here. Yes, please. Any problem or any doubt? Okay, thank you so much then. Thank you so much then everyone for joining the class. Let's meet in the next class. Thank you so much.